On a clear dark night, thousands of stars can be seen in the sky. And not just stars. Light from a vast range of celestial objects travels to us from long ago and from far away. How can we make sense of the universe? What can we discover from the radiation reaching us from the skies? The sky does not look uniform at night. If the night is particularly dark and clear, we can see a faint, irregular band of light stretching across the sky, the Milky Way. To understand observations like this, we must travel in our imaginations a long way out from the Earth in its orbit around the Sun. The solar system, after all, is little more than a number of planets revolving around a rather insignificant star. The Sun is just one of the thousands of millions of stars that go to make up our own local galaxy. A galaxy in the common shape of a spiral, with the solar system lying in the outer regions. Our galaxy is 100,000 light years in diameter, and it's not stationary, but slowly revolving, once every 100 million years. The Milky Way is just the view we get of our own galaxy from our place towards the edge. It's tempting to think that our galaxy and our place in it are in some way special, but they're not. Billions of other galaxies of all shapes and sizes are found in the universe. But in this program, our concern is with the stars that make up the galaxies and not with the galaxies themselves. Stars form from the medium between them, interstellar gas and dust. But how do they form? For how long will they shine? And what becomes of them when their fuel is spent?
To answer those questions, this is the graph we need. We have to follow the evolution of the interstellar medium through enormous changes in density and in temperature. The horizontal axis is temperature, a logarithmic scale starting at just 1 Kelvin on the left and proceeding in steps of a factor of 100 to reach 10 to the 8th Kelvin on the right. The vertical axis is density, again on a logarithmic scale, starting at 10 to the minus 20 kilograms per cubic meter at the bottom and rising in enormous steps of factors of 10 to the 10th to reach 10 to the plus 20 kilograms per cubic meter at the top. I'm standing at my proper starting place on such a plot, a point representing the Earth. It's an average temperature through its volume of about 1,000 kelvins and an average density of about 5,000 kilograms per cubic meter, 5 times that of water. The Sun, on the other hand, has a rather lower average density, partly because it's got more light gases, hydrogen and helium, and partly because it's hotter. But the range of temperature and density is really too big to show it just by a single point for the average. So I'm going to show it with a line, starting from about 15 million kelvins, the temperature of the core, and going down as we go outwards through the star to about 5,500 kelvins at the surface. So, remembering we have increasing density up the vertical axis and increasing temperature along the horizontal axis, the Earth is plotted here, taking average values, and for the Sun, we can plot the core here, joined to the point for the outer regions here at much lower densities and temperatures. But to understand how stars form, we must start in the medium between the stars. It's very low density and consists typically of a gas made up largely of hydrogen and helium and a trace of dust that accounts for much of the heavier elements. But the interstellar medium is far from uniform. For instance, here's a rather dramatic part of it, the Veil Nebula. It lies in our galaxy, not far away from us by cosmic standards, and it's quite young, about 30,000 years old. But it's expanding outwards, so it's not a likely site for condensation into stars. We have to look elsewhere in the interstellar medium for that. Where on this plot would we find the interstellar medium, which is the starting point for making a star? Well, certainly we have to go down in density. This is the level which in a laboratory would be thought of as a good vacuum, about 10 to the minus 10 kilograms per cubic meter. But the Veil Nebula is much lower down still, more like 10 to the minus 20 kilograms per cubic meter. Other parts of the interstellar medium might be a bit cooler, but almost as tenuous. Gravity, acting over astronomic times, pulls this tenuous matter together to make stars. Gravity pulls each particle in the universe to every other particle. Over cosmic distances, it's the only force of importance. It takes about 100 million years or so to pull the matter together. And then there's a very rapid final stage, just a few million years, when the cloud heats up and a protostar is formed. Gravity doesn't have it all its own way in that final stage. It has to battle against other influences which tend to expand the cloud. For instance, consider the effect of temperature.
For the interstellar medium, the kinetic temperature is a measure of the average speeds of the atoms and molecules as they move around at random. At high kinetic temperatures, most particles have high kinetic energy. The only force binding these particles together in the interstellar medium is gravity. If the temperature were even higher, this body could not exist. The individual particles would disperse. At lower temperatures, most of the particles have less kinetic energy, so they crowd together more easily under gravity. For a given body, the effect of raising its temperature is to cause it to expand. The increased kinetic energy more effectively opposes gravity. Even for a gaseous body which is not obviously dispersing, the most energetic particles can overcome gravity and escape. However, for a given temperature, mass, and composition, the denser the body, the fewer the number which can escape. Indeed, throughout the whole of a denser body, gravity has a greater influence, simply because the particles are closer together. So the best place to look for star formation are regions which are comparatively cool and dense, certainly denser than the Veil Nebula, which is over there. For example, about here, at temperatures of, say, 50 kelvins, densities 10 to the minus 15 kilograms per cubic meter. Now, such regions are known in space. For example, this dark region in the North American Nebula, or another example, this dark place, the Coalsack Nebula. Now, astronomers call these regions dense clouds. They consist mainly of hydrogen in molecular form, and this leads to their alternative name, molecular clouds. Now, dense clouds don't actually emit very much radiation, so you might ask, how do we know that they are there? Well, the most obvious way is that they obstruct light from the stars beyond them. For example, here is part of a dense cloud in the constellation of Orion, in an arm of our own galaxy. It's called the Horsehead Nebula for obvious reasons. To make the picture clearer, we can remove the stars between us and the nebula to leave this. The lower half of the picture, and the Horsehead itself, which measures about 2 light years from front teeth to back of head, is part of a dark, dense cloud. The stars beyond are obscured by the dust particles in the cloud. The red tint in the upper part of the picture is radiation from the gas in a region outside the dense cloud. Stars nearby heat this gas, and the emission spectrum is dominated by the visible Balmer lines of hydrogen, hence the red tint. Dense clouds can be vast, with enough material to form tens of thousands of stars or more. So when the clouds contract, they will form very many stars. Therefore, the cloud must break up as it collapses. There's just too much material to form only one body. In fact, some astronomers believe that the Horse's head exhibits an early stage of fragmentation. So if clouds do break up, then we would expect to find clusters of stars. And indeed, such clusters are known. For example, this is Omega Centauri, about 620 light years across and containing perhaps as many as 1 million stars. And here's another example, 47 Tucanae, with similar dimensions. Now, these clusters are amongst the oldest objects known to astronomers, perhaps as much as 10,000 million years. They are known as globular clusters. Now, open clusters are also known, and this is a famous example, the Pleiades. And that blue haze is material being lit up by the stars, material left over from the dense cloud. So it does seem that dense clouds do lead to star clusters. However, if we just consider density and temperature, then gravity seems to win too easily and would lead to too high a rate of star formation. In any case, there's observational evidence that dense clouds are not collapsing, or at least not collapsing very fast. Fortunately for our story, there are influences which can slow down collapse. For example, rotation.
If two cloud fragments happened by enormous coincidence to have exactly zero rotation with respect to each other, they would simply collide head-on and coalesce under gravitational attraction to form a larger fragment whose overall angular momentum would be zero. But normally, two fragments start with some overall rotational motion with respect to each other, and they do not collide head-on. They can still merge to form a single fragment, but with an overall rotation, tending to prevent the individual particles collapsing together as fast or as far as they otherwise would. So with rotation, dense clouds collapse more slowly than without. Magnetic fields and other influences can also slow down collapse. These influences which hinder contraction may be so effective that it takes some external compression to start the collapse. Once started, gravity takes over, so some transient compression, like a passing pressure wave, may be enough to start the collapse and the fragmentation. Within each fragment, the infalling matter slowly gains speed, gains kinetic energy. But when the fragment begins to heat up, that gain in energy is offset by energy radiated out into space. At some time during this stage, there's a very significant change in the interior conditions in the fragment. That's when the opacity rises high enough to hold back, to bottle up the radiation, and then the temperature rises very fast to hundreds of thousands, up to millions of kelvins. So with this final increase in density and rapid increase in temperature, the pressure becomes high enough to balance the force of gravity. This is the final stage in making a protostar. So now what happens? Well, if gravity were the sole source of energy in stars, as indeed it is in the protostar, then a star could only keep shining as long as it kept contracting. And a star of the mass of our sun could only keep shining for about 10 million years. But we know for a fact that the sun has been keeping the Earth warm for about 5,000 million years. So there must be a fuel which has been supplying the energy to heat the star and keep it supported all that time. What can that fuel be? Well, let's first take stock of the conditions under which the fuel must operate. A temperature of 10, 15 million kelvins and densities of about 100,000 kilograms per cubic meter. And what are the possible fuels? Well, not many, because the star is made mostly of hydrogen with some helium, about 15 times as many hydrogen atoms as helium atoms, except I shouldn't really say atoms, because under these conditions the electrons are stripped off atoms and we have bare nuclei swimming in a sea of electrons. Matter in this very highly ionized form is an example of a plasma. In the hot plasma, the nuclei have high random velocities, and when they collide, they may undergo a nuclear reaction. In fact, the speeds of the protons are just about high enough for them to fuse together in a series of reactions which ends up producing a helium nucleus and releasing a lot of energy. So it's a nuclear fusion which supplies the energy to keep the star hot and, for the time being anyway, to support it against gravity.
We have seen how gravity dominates the birth of stars, the most obvious single bodies in the cosmos. As we leave the Earth, we might look back and wonder, where does a planetary system such as ours come from? The answer seems to be that planetary systems are formed from leftover material from the protostars. That raises the exciting possibility of other planetary systems and of other planets bearing life. But it also focuses our attention on this leftover material, and in particular on the fact that compared to the early universe, it is enriched in elements other than hydrogen. How did this enrichment come about? To answer that, we must move on hundreds, even thousands of millions of years from star birth to star death. Now, at this stage, the hydrogen fuel in the core has pretty well run out. There's a bit of action at the surface, but this doesn't generate enough thermal motion, enough pressure to oppose gravity. So, what happens next? Well, that depends on the mass of the star. So let's start with stars of about a solar mass. The core begins to contract under gravity. And this has the effect of driving out the envelope. It expands in radius by 20, 30, 40 or so times. And as it expands, it cools, and in a few 100 million years, we have a red giant. Meanwhile, inside the red giant, conditions in the core have taken us to about here on the density temperature diagram. This density is about the highest that we've so far encountered. And in reaching it, the heat released has given rise to a whole new set of nuclear reactions which heat the core. Now, at this point, the core has certainly stopped collapsing. And these nuclear reactions, these new ones, have certainly played a role in that. At this stage, in stars of about a solar mass, an interesting condition of matter becomes temporarily established in the central core. The electrons there become what is called degenerate. One consequence of this is that core contraction is strongly resisted by electron degeneracy pressure. However, at this stage, it is not this that halts the contraction, but new nuclear reactions in the core made possible by the now higher temperatures there. In the main, these reactions use helium as a fuel to generate yet heavier elements. As the helium in the core is used up, the core contraction resumes. Eventually, possibly after further nuclear reactions, the core and part of the envelope contracts until electron degeneracy pressure halts the contraction. We get a hot blue Earth-sized star. The rest of the envelope is expelled to form a hot expanding shell of gas, often enriched in elements other than hydrogen, particularly in the case of more massive stars. Here, for instance, is the Ring Nebula in Lyra, first seen in 1779, but still with a shell visible around it, expanding at 19 kilometers per second away from the dying star. For the shell, gravity has lost. The expanding shell will disappear and enrich the interstellar medium while the core star cools and dims. As it cools and dims, it becomes white and is then called a white dwarf. It continues to cool and dim, and ultimately it becomes a black dwarf, and a mere 100 million years or so have elapsed since it was a red giant.
The transition from red giants to white dwarfs has taken us from here to here, the highest densities yet. But so far we've only considered stars of solar mass. What about more massive stars? Betelgeuse, the top left-hand star in the constellation of Orion, is 20 times as massive as the Sun, and it's very large. It's one of the largest stars in our neighborhood. It's bigger than a red giant, and it belongs to a class of stars called supergiants. When its nuclear fuel runs out, electron degeneracy pressure will not be enough to support the core. The core will collapse with a violent release of gravitational energy in a huge explosion called a supernova, in which the star flares up to millions of times its normal luminosity. In the explosion, the atmosphere is thrown off, and we've seen what that expanding remnant of the envelope looks like 30,000 years later, the Veil Nebula. Another example is the supernova observed in 1054 and recorded by Chinese astronomers. Its remnant is visible today as the Crab Nebula. And from 12,000 years ago, the Vela supernova remnant, 1,500 light-years away in the southern sky. In the center of the Vela remnant, we can see what remains of the original star. It doesn't emit much light, but it emits radio waves which we receive in the form of pulses, about 10 per second, and it's called a pulsar. Several hundred pulsars have been found, with periods ranging from a few milliseconds to a few seconds. And it seems that pulsars are very compact stars rotating very rapidly, and that their radiation is beamed out like a lighthouse, which is why we see it in the form of pulses. And it's thought that pulsars are made mostly of neutrons, because then we can understand how they can be so compact and so dense. The point is that neutrons can exert the so-called degeneracy pressure, like electrons, but the neutron pressure can be high enough to support a star which is only a few kilometers across with a density of 10 to the 18th kilograms per cubic meter. But gravity can win even over neutron pressures. If the mass of the compact body is more than 2 or 3 solar masses, then theory predicts that nothing can stop it collapsing down to a black hole, a body of more or less infinite density from which not even light can escape.
But that has never been seen. It's based on a model, and that model is based in turn on observations of other stars. Observations are hard won in astronomy. They need big telescopes, expertly used. This is the newest large telescope in the world at the moment, the Isaac Newton telescope, high on an extinct volcano on La Palma, a fine modern telescope with modern electronic detectors. The internal structure of the objects that we've been showing have to be somehow deduced from the faint light picked up literally photon by those detectors. How different that is from the study of the Earth, where we can make all the observations we like on the surface, yet we're still not at all sure what the interior of the Earth is like. To deduce from the point-like image of a star a model of what the core of the star is like is truly an amazing feat. Astronomy advances from an observation to a new model to further observations. Here is the next stage on La Palma, the William Herschel telescope, neighbour of the Isaac Newton, but with a mirror half as big again.
To understand matter in the universe, we'll look one by one at the stages in the cycling of matter between stars and the interstellar medium. Gravity is the driving force, and its energy too is cycled, released during contraction, absorbed during expansion. We can only see that broad picture if we look not on a human, but on a cosmic timescale.
Let's think of our galaxy as a clock. It turns once every 250 million years. Clouds contract in a fraction of a turn. The final stage of contraction, heating up to form a protostar, is almost instantaneous. A star like the Sun shines for many turns, but its energy is lost in the immense spaces of an expanding and cooling universe, and the star dies. But that is not the end. Eventually, after about 1 million turns, all stars are dead and have collided to form an object so massive it must collapse to form a gigantic black hole. Nuclear energy will delay the end, but in an individual galaxy, gravity will win.